This is Unit 1, Video 9. In this video we will talk about electron configuration, which is a way of expressing how electrons are arranged around an atom. And it's going to look something like this. It'll have numbers and letters and small numbers. So we'll read this as 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. And down here it says that we fill lowest to highest energy levels. And there's a name for this principle. It's called the Aufbau principle. What it essentially says is if we have, say, 3 energy levels, and we are going to put a bunch of electrons in there, we will fill the first closest electron level, the one closest to the nucleus first. Once that one's filled, we'll fill the next one. Once that one's filled, we'll fill the next one, and so on and so forth. So this may sound very logical, but the idea is we never start on the outside, we always begin on the inside, and only when that's filled do we go to the next level. And here is what it will look like. The big number in front represents the shell, so this is the shell. Remember, the shell is also called the energy level. The letter will represent the subshell, also called the sublevel, and the number, it's going to be a superscript up to the right, will be the number of electrons. If you recall, when we wrote ions, we put, say, -2 up here, and that represented essentially the number of electrons. So this is kind of in keeping with that idea. And that will be the number of electrons in the subshell. So in this case, this configuration shows the second shell in the P subshell has 5 electrons. Okay, so we can ask a question. Here is a configuration of an element, and the question is, which atom does this configuration represent? So what we can do is total up the number of electrons, because these are, remember, electrons. If we total those up, we've got 2 here, plus 2, that's 4, plus 6, that's 10, this gives us 12, this is 18, and this is 20. So we're just asking ourselves which element is element number 20, and that element is the element calcium. So calcium is the element that this configuration represents. Pretty simple. Next, we're going to have you try it to do the same thing here, and then we're going to learn how to write these ourselves. Now, before we do that, the periodic table actually has all the information necessary for us to write these configurations. We're going to break the periodic table up into 4 blocks, and these correspond to the subshells of the blocks. So the S subshell is represented by the S block. Notice that this is 2 elements wide. That's because the S subshell can hold 2 electrons. The D subshell, right in the middle, will hold 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's because the D subshell can hold 10 electrons. The P block is on the right, and it holds 6 electrons. 3, 4, 5, 6. And then finally, the F block down here holds 14. 2, 4, 6, 8, 10, 12, 14. Now, the n-1 and n-2 here actually shows you something about the energy levels of the D and the F subshells. You'll notice that the S subshell has a 4 right here. That means we are in the 4s subshell, meaning we're in the 4th energy level. And sometimes you'll see the periodic table has a 4 right in front of it, and 5 down here, due to the energy levels. Now, when you get to the D block, that energy level is reduced by 1. You go down to 3. So this right here, for example, if you were to represent this electron, this would represent 3d3, a 3d3 electron, because it's the 1, 2, 3 third electron in the D subshell. But we don't put 4, it does not correspond to the overall energy level. You go down 1. And likewise for the F block, you go down 2. So now the F block, if you take a look at the periodic table, the F block fits right in here. And so if you were to do this element, it would not be 6F, you'd subtract 2, this would be 4F, and it'd be 4F2, because it's the second element in the subshell. We're actually going to use this, so if you look at the periodic table, make sure you can visually see the 4 subshells, because this will be the key to writing these electron configurations. Alright, let's go ahead and do a few. What is the electron configuration of sodium? So let's go ahead and consult the periodic table to help us do this. So first, find sodium. Here is sodium on the periodic table. Notice it ends up in the 3rd shell and in the S subshell. We'll recall that this is the S subshell, this is the P, this is the D, and the F we won't have to use, but the F would fit right in here. So now, what we'll do is we'll begin all the way at the top. We're actually going to essentially fill all the electrons from here, and we'll pretend that helium is sitting right here. It's sitting on the right, but we'll essentially go through those two. Then we'll go through these two, we'll go through these 6, and we'll end up at sodium. So everything that's been marked, and you can say that helium has been marked, we'll have to write the configuration for. And it goes like this. The one in front is what we begin with. That's the shell, so 1. And we're first going through the S subshell. So we'll do S, and there are 2 electrons there, so we do 1s2. Once we're finished with that, we go down to the 2 subshell. We'll put that down, and then we'll have to go through the 2s elements of that subshell. So 2s2, then on to the P, and here we have 6 elements, 1, 2, 3, 4, 5, 6, corresponding to the 6 electrons in the P subshell. It's still a 2 because the 2 actually corresponds to both the S and the P. So we have 2P all the way out to 6, and then finally we're going to stop at 3S1 because this is the first element of that subshell. So 3S1 is where we stop. And it's as simple as that. If you take a look, the very last electron usually corresponds to the position where we stopped, which is the 3S, and this is the first position, 3S1. Alright, we're going to do another element just to practice. Let's go ahead and do the element zirconium. Zirconium is a little further down in the periodic table, will allow us to go through a few more of the subshells. So let's find zirconium. Here is zirconium, element number 40. So what we realize is we'll have to go through essentially beginning at hydrogen all the way through to zirconium. And we'll do it the same way we did it earlier. So we'll always begin the same way, 1s2, and that corresponds to the first 2 elements. And then we'll go down to 2s2, onto 2p6, onto 3s2, onto 3p6, and then 4s2, and then onto the D. Now, remember that the D is n-1, so this is actually 3D, not 4D, 3D. So we'll have to do 3D, and there are 10 electrons, so we'll do 3D10. And then finish up with the P. We're back to 4P, because remember this 4 applies to both the S and the P, so we'll do 4P6. On to 5s2, and we're almost finished. Again, this will be 4D2, not 5D, but 4D, because you go 1 less. So 4D2. And that is the configuration of the element zirconium. Hopefully you followed right along. Take a moment and do 2 of these on your own, carbon and iron. Now, there is a way to shorten this using what's called noble gas notation. So what we'll do is, some of these elements have really long configurations, and there's no reason to write all of it. It's only necessary to write really the outside part of the configuration. So we'll use the noble gas that comes right before the element. Now, let me show you where the noble gases are. The noble gases are actually the very last group on the periodic table. So here's your periodic table, and as you'll see, the noble gases are the very last group. We'll put that in brackets, and that will represent a part of the configuration. So here is an example. What we've got is we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now, if you take a look, this configuration right here is actually 18 electrons big, so 2, 4, that's 10, 12, 18, and that actually belongs to the element argon, because the element argon is element number 18. So this whole configuration can actually be placed in brackets with simply argon in those brackets. So the reason why we do this is because argon represents what are called inner shell electrons, and these inner shell electrons will not be reacting. It's only the outer shell that we'll care about. So that's why we're able to do this. So all we have to do is carry over what was not in the brackets, and our final answer is argon in brackets 4s2. Now that simplifies it quite a bit. Let's practice some of these. Let's go ahead and write the noble gas configurations of both sulfur and copper. So consulting the periodic table again, let's do sulfur first. Here's sulfur, element number 16. Now the noble gases are the last group, group 18. Here they all are. Part of the reason why they're called noble gases is because they are unreactive, they're very stable. And so that's why we use them for this configuration. So the rule says go back until you hit the previous noble gas. Now the previous noble gas to sulfur is actually neon. So we'll put neon in brackets for sulfur. This will be the configuration of sulfur. Go ahead and put neon in brackets. And then simply whatever comes after neon we'll have to consider and write down. So that's these two electrons, which are 3s2. And then these 4 electrons, which are 3p4. This is the configuration of sulfur, the noble gas configuration of sulfur. All right, let's go ahead and do the other one. And the other one was it copper? Yes, it was copper. Let's take a look at copper. Element number 29. Do the same thing. Find the noble gas that comes right before it, and that noble gas is argon. So for copper, we'll go ahead and put argon in brackets, and then list whatever comes after argon this way. So we have these 2 electrons, which are 4s2, and then we have to go through all of these electrons until we get to copper. Now that's actually 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. So it'll be D9, but remember again, it's 3D, not 4D. So we'll do 3D9. Now, if you ever look up copper's configuration online or in a textbook, they'll actually show not this configuration, but a configuration that's a little different. And I'm going to show you that here and why. What happens is some of these elements, like copper, have the s electron actually jump into the d subshell and fill the d subshell. So what happens is instead of writing it like this, copper is written as argon 4s1 and 3d10. Now this is called an exception to the filling rule. And this exception actually happens for these elements here. And the reason this happens is because an element is more stable if it can fill a d subshell completely. And we have experimental evidence of this. This is actually how copper fills its electrons. So we'll talk about a few of these exceptions, and we'll have you know just a few of them. In this case, these 3 are going to be required for you to know that these are exceptions, and we'll show you some of these exceptions as we go along. But there's not a lot of them. Every rule has an exception, is what we say in science. So those are going to be the exceptions. All right, go ahead and try a few of these on your own. Do nitrogen and bromine, and then we'll come back and talk about orbital notation in the next lesson.